Hey folks, welcome back. So we're going to be talking about sinusoids, and this is coming off of our conversation about the unit circle and how we can determine the terminal points of a unit circle using different trig functions of a general right triangle that we form using the unit circle. Sinusoids are like a really cool part about trig. You end up forming some really cool graphs, and so I actually, when I was first learning this, I thought that this was one of the coolest parts about trig other than the unit circle. But sinusoids are just a fancy way of saying it's a family of curves based on the graph of the trigonometric functions sine or cosine, right? So we can also categorize sinusoids as another type of function group called periodic functions. And periodic functions are just functions that repeat after a certain interval. So you're going to see the same look or design over and over again on the graph. And so we create sinusoids by taking the central angle measure, typically in radians, right? And outputting the corresponding trig value. You can do it in degrees. It doesn't really matter. You're going to end up getting the same terminal point value. But just because most of our work going forward is going to be in radians, I would just recommend that you find these values based on radians. So back in Unit 1, when we were exploring the unit circle a little bit more in depth, we explored these really famous central angle measures, right? And the reason why we explored them is because each of them have very important terminal points on our unit circle. And so these terminal points correspond to whenever this line that we draw from the origin until it hits the circle at an angle of whatever this angle is, like pi over 6, right? Whatever that point is that lands on the circle is going to be our terminal point. And so these points were really famous because we found that there was some kind of pattern to them where they ended up repeating every time we did a revolution of the circle. And so we developed, through a proof of a right triangle inscribed within a unit circle, and we're able to prove that for any general right angle that's formed within a unit circle, the y value, or the y coordinate, is going to correspond with your sine of theta value. And so we know that sine of theta is going to correspond with our y coordinate value of whatever our terminal point is. So let's look at this, right? If I'm at 0 radians, right, I'm right over here, right? And so I know that from my origin right over here, I am moving 1 unit to the right, and I'm not making any vertical movements up or down, right? Because we know that each radius is worth 1 unit in a unit circle. And so over here, this coordinate is going to be 1, 0, right? And so my y coordinate of that point, 0, is going to correspond with sine of 0. I'm going to focus on just pi over 2, pi, 3 pi over 2, right? Like the angle measures that correspond with axes, just because I think that those are going to be the most straightforward. We're not dealing with any fractions or anything like that. And we still get to see the general shape and period of the function. So let's focus on pi over 2 now, right? So from the origin, I'm just moving 1 unit up. I'm not making any horizontal movement right or to the left. So this coordinate is going to be 0, 1, right? And so I have a y coordinate of 1, so that's going to correspond with my sine of pi over 2. For this point right over here, right, I'm making 1 unit to the left from my origin. So this is going to be -1, 0. So I'm going to be at 0 again. And then for 3 pi over 2, right, I see that I'm moving 1 unit down. I'm not making any horizontal movement. So I'm going to be at 0, -1. So my y coordinate, -1, is going to correspond with sine of 3 pi over 2. And so once I get to 2 pi, I see that everything starts repeating itself, right? Because I've made a full revolution around this unit circle. So I go to 0, 1, 0, -1, 0, right? And so I really just need these 5 values in order to, plot out my sine curve. And so let's actually plot that out and see what the sine curve should look like. So realizing that this is our table for sine values, right? I'm always going to start at 0, 0. So that corresponds with this point right over here. So I'm just going to plot that right over here. And then I'm at 1 for my y at x equals pi over 2. And then I'm back down at 0. And then I'm down at 3 pi over 2 to negative 1. And I'm back over to 0. And then I see that that repeats over and over again. So I'm just going to keep this pattern going over and over again. I could even do that going into the negatives, right? So this is going to be like this right over here, right? I'm just continuing this pattern over and over again, right? So I'm going to start at the origin, and I'm going to start making my curves, right? Because I'm making a curve, they should be curvy, right? So I'm just going to keep following this. I'm going to draw arrows at the ends to indicate that I'm going on forever and ever and ever, even beyond what you see on this graph, right? And so this is what your basic sine function looks like. It looks like it's a wave, right? So sometimes sine functions or sinusoids are called wave functions as well. So when we look at the sine function, right, we want to think about, what are some characteristics of it? So what are some things that make the sine function and not any other type of function? And so one thing that we want to inspect is the domain. So what are the possible inputs available, right? So we want to look at the end behavior of this graph. And so I see that we're going off to the negatives for infinity in our input values. We're going off into the positive infinity input values for our function. And so all real values, right, should work over here, right? So all real numbers should hold with the sine function, right? And our range, we have to inspect what is our minimum and maximum output values, right? So for our output values, that corresponds with our y-axis. And I see that the lowest value I have is -1, and the highest I get is 1. And so my range is going to be from -1. I do hit -1, so that's why I would put the bracket right next to -1, and all the way to +1. And once again, I hit +1, so I'm going to put a bracket after it. If I didn't hit 1 and I didn't hit -1, if I approach those values, then I would be putting the parentheses instead. My period of my sine function is really asking me how long does it take for me to have one wave, right? And so we were showing in our table that if we started at 0, made our way over and up, right? Right at 2 pi is when things start repeating itself, right? Because we've made a full revolution around that unit circle. And so because it takes me from 0 to 2 pi in order to make a full revolution of that unit circle and show that full wave of my sine function, my period is going to be 2 pi. Let me change the color. 2 pi. Great. Now my amplitude is asking me how far up does it go from my center line. So how far up does my function go from my center line? And so if I'm looking at this function of sine of theta, right, I see that my center line, or what cuts my function in half, is my x-axis over here. So let me just highlight that really quick. Okay, whoops. So I want to inspect from my center line, my x-axis, how far up does my function go? And I see that my function goes up 1 unit, so my amplitude would be 1, right? If this were to go all the way up to 2, right, so like let's say that my function were transformed so that the wave was twice as high, right, that my amplitude would be 2 because it's 2 units from my center line. And I know that this is my center line because the amount that I'm going above my center line is the same value as how much I'm going below my center line, right? So this is going up 1 unit, this is going down 1 unit, because they're both a change or difference of 1 unit. I know that that's actually my center line. So let me erase this just so we can see this a little bit clearer. Okay, and then my final question is asking me to find where sine always starts, right? And so one key characteristic of sine is that sine always passes through the origin. And so that's usually like where I like to start my table of values, because I know that that's typically where sine should go. So if it passes through the origin, then we know that it's definitely going to be a sine function. So we always start sine of theta at 0, 0. You don't have to start it there, but that's a good indicator to show that you're dealing with a sine function and not like a cosine function. So another key characteristic of our function that we want to look at is we want to see if there's maybe any symmetry that's going on. So that means that if I fold or rotate my function at a certain point or maybe at a certain axis, then when I do that fold or that rotation, it's going to fold right on top of each other or map right on top of itself. And so let me explore what that means. So if this were an if this were an even function, that means that if I took my y-axis and I folded this paper in half directly over that y-axis, then this function would map directly onto this function. So this would go right on top of this side right over here, right? You can actually, if you can print out these notes, you can actually try that out for yourself. That doesn't actually happen though, right? Because let's look at this a little bit more clearly. So if we have this y-axis, right? Let's look at this first peak over here, right? This first peak is, let's see, it's pi over 2 units away from our y-axis, right? But then if we go negative pi over 2 units to the left of our y-axis, we don't see that same peak over there, right? And so if we were to fold our paper in half over this y-axis and they were actually symmetric, right? And if that were our line of symmetry, then you would have a peak that would fold right over here. And we don't have that, right? So we know that this function's not even. So we actually say that this function is odd. And to be an odd function means that you have symmetry about the origin, right? The origin is really important for sine functions. And so that means that if you were to rotate this function about the origin 180 degrees, right, you would see that you would have a graph that overlaps exactly with our original sine function over here, right? So I know that that's a little bit difficult to explain. I'm having difficulty explaining it, and so I created this Desmos graph right over here for you to kind of explore what that means a little bit more. And there are some prompts to help guide you through how to use that Desmos activity. So yeah, definitely try that out. I'm gonna put that in the caption of this video. Yeah, so if you have any questions, just feel free to email me, and hopefully you found this helpful. So yeah, good luck.